So oftentimes we're given a reaction and we're asked to do several things with it. First of all, we may be asked to classify a reaction. So there's many different ways to categorize reactions, but a very common one is to classify them as either a reduction oxidation reaction, an acid-base reaction, or a precipitation reaction. We also may be asked to take a reaction that occurs in aqueous solution and write it as a full ionic equation where we actually show how things like soluble salts split up into their individual cations and anions. And finally, we can take our full ionic equation and cancel out spectator ions to make a net ionic equation. So what I'd like to do is to look at an example reaction and just go through these steps with you. Okay, so in this equation, for this reaction, we've got water, and we've also got some sort of organic compound. Looks like it's got an alkene and a alcohol group on it, and it's reacting with potassium permanganate to form manganese dioxide and some looks like a trialcohol and some potassium hydroxide. Great. So we have to somehow classify this reaction. Now, an important thing to remember is that if any oxidation numbers change for an element, you know it's a redox equation. So that's the first thing you should check. Okay, so before you check to see if it's acid-base or if it is a precipitation reaction, look to see if any elements get oxidized or reduced. So first, let's look over here. We've got potassium. We know that's in its +1 oxidation state. And we see over here B+1, so that's not changing. We've got oxygen. We know that's -2. It's -2 over here. Hydrogen's +1. Here it's +1. So there's no changes there. But let's look at some of the more interesting atoms. Let's look at this manganese atom here. We know this compound it looks like it's got manganese and oxygen. So we know oxygen's normally -2, and there's 2 atoms. So this whole, the total charge supplied here would be, or oxidation number would be -2 times 2. So whatever's on this side has to supply a +4. So we know that this is a +4 oxidation state. This is, we'd say, manganese 4. If we look at this compound over here, we can see that we've got 4 oxygens. So we've got 4 times -2. We've got 1 manganese, let's just call that X. We've also got a potassium, that's +1. All of that has to equal 0, right? Because potassium permanganate as a compound, we know, is going to be just neutral. So all of this has to equal to 0. So we've got -8 plus X plus 1 is equal to 0, and we could just say this is going to be -7, so if we move it over to the other side, we get +7. X is equal to +7. So this is manganese 7. So we went from manganese 7 to manganese 4. So we can see what happens when we reduce the value of our charge. That's reduction. So our manganese atom got reduced. So as soon as you see that one element is being oxidized or reduced, you know right away it has to be an oxidation reduction reaction. Okay, so it's always going to be classified that way if you're doing that kind of oxidation or reduction. Incidentally, notice we could get the same information if we split up our potassium permanganate into potassium ion and permanganate ion. Because if we look at this ion, we've got X. We're adding 4 oxygens to it. Each one's -2. And we can see that has to equal not 0, right? Oh, it equals -1. So now when we solve for X, we've got X -8 is equal to -1. So it must be that X is equal to +7. So with ionic compounds, even if you just split off the individual ions, that's sometimes a faster way to calculate the oxidation numbers, but you could do it with the compound too. You'll get the same answer. Okay, so the manganese was reduced. So now something else has to be oxidized. And right away, we might zoom in here and say, wait a second. We see some carbons here that weren't bound to oxygen, and now they are. And that's always a sign that, anyway, we should suspect oxidation here. And so let's go ahead and on a separate page, let's look at the oxidation numbers for carbon for the atoms that are reacting. We can see this carbon over here, nothing's really happening to it, right? It has a alcohol, it still has an alcohol, nothing's happening to it. So really this is the reaction center here, right? So let's go ahead and draw that on the next page and look at its oxidation numbers. Okay, so first we draw the molecule in its reactant form. And to do oxidation numbers, it's probably safer to go from the line angle to the full-on Lewis structure, just so we don't forget the implicit hydrogens. So we know we've got a bond to a hydrogen here, we've got a bond to a hydrogen here, we've got a bond to a hydrogen here. We can even remind ourselves that these are carbons. Okay, and we don't really care about the other hydrogens on this methyl group because this is the reaction center. We know that this is a carbon, that's all we care about. All right, let's go ahead and analyze the oxidation numbers. Now remember, for oxidation numbers, you attribute the electrons to the more electronegative atom. So carbon's more electronegative than hydrogen. Okay, these are split evenly because it's carbon on both sides. Same thing over here. So we take the valence on carbon, that's 4. We subtract the electrons within the circle, so we've got 1, 2, 3, 4, 1, 2, 3, it's half a bond. 4 and 5. Okay, we can do the same thing over here. All those electrons, all these, and half of the ones in the double bond. So we get 4 minus 1, 2, 3, 4, 5, 6. Okay, so those are our two oxidation numbers before the reaction. We draw the compound after the reaction. Remember, we were taking these carbons, and this one already had a hydroxyl on it. I'll go ahead and draw the rest of the structure just to show you that that part's not changing. But we're adding an OH group here. So we're breaking our double bond and we're essentially adding OH groups. Okay, so these junction here, of course, are carbon, carbon, and carbon. So this is our product molecule. Let's go ahead and do those oxidation numbers here. So because oxygen's more electronegative than hydrogen, we don't get any of those electrons. We split this bond in half, we split this bond in half, we get all the electrons on the hydrogen. Okay, so for this carbon, we get 4 minus, let's see how many electrons, 1, 2, and 3, 4. 4 minus 4, an oxidation state of 0. So notice we went from -1 to 0. So we're going up in oxidation state. So we can see we're getting oxidized. And that's good because, of course, the manganese was getting reduced. So something else has to get oxidized. What about this other carbon? So we don't get any of these electrons. We get both of these. We get both of these. We get 1 on that bond with carbon. So we would say a valence of 4 minus 1 electrons, 2, 3, 4, 5. So we went from -2 to -1. Once again, we're going up in oxidation number. We're becoming more positive, or really just less negative. So this is definitely oxidation. So our carbon is being oxidized. Each carbon is being oxidized by 1. And if we go back to our manganese, we saw that it was being reduced. So we'll go ahead and put that on the other slide. So we're being oxidized. Okay, great. So we have we figured out what's being oxidized, what's being reduced. we might as well throw a little extra vocabulary in here. We might want to say what is the reducing agent and what is the oxidizing agent. So if you are being reduced, then you oxidize something else. So we can use that language here. We can see that the manganese is being reduced, and so it oxidized the organic compound. So we can say our potassium permanganate is the oxidizing agent. Okay, so notice the oxidizing agent is a thing which is itself reduced because it oxidizes something else. All right, what about the organic compound? Well, it's being oxidized, which means it's reducing something else. And so we can say that the other reactant is our reducing agent. So notice when you're talking about oxidizing and reducing agents, you're always talking about reactants, right? They're things that do something to something else, right? So our organic compound here is going to be reducing the other compound. In the process, it gets oxidized. That's sometimes a little confusing for students, so I thought I'd mention that. Okay, so we've classified our reaction. And once you've figured out that things are getting oxidized and reduced, you can stop. You don't have to worry about being classified as a precipitation reaction or a acid-base. So in some oxidation reduction reactions, we produce a solid, and that's something we did right here, right? We can see we produced a solid here. We don't classify this as a precipitation reaction, right? So if you see this on a test or quiz and you have to choose one of those three categories, choose oxidation reduction, okay? Notice that also you might produce or consume acid or base. That's irrelevant in terms of how we name these. It's the oxidation reduction nomenclature is going to take precedence over acid base, and so you just ignore any acid base and just classify it as a redox equation, okay, because that's really what they're asking. Okay, so let's go on to the next thing, which is to go ahead and break this down into ions and see if we can make a full ionic equation and a net ionic equation. So let's do this step next. All right, let's write this out as a full ionic equation. So what we have to do is anything that separates into separate cations and anions in solution, we have to write it out separately. So water does not, so we just write, we got 4 waters. And because phases matter when we go to cancel to make the net ionic equation, always include your phase labels, whether it's aqueous or solid or liquid or gas or whatever. Okay, so we've got 3 of these molecules here. Those are also aqueous. We've got 2 potassium permanganates. Okay, now we look at this and say, okay, wait, this is an ionic compound. And it says that it's aqueous. And that should not be a surprise to us, right? Because if we look at our solubility rules, we say, hey, this cation tends to make soluble salts. So this should dissolve in water, and that's what the label says anyway. So we're going to split this up. When we split it up, we have to remember stoichiometry. There's 2 potassiums in here, but there's also 2 permanganates, right? There's 2 of each, right? This coefficient applies to the whole thing. So we've got 2 potassiums. We've got 2 permanganates. Oops. Let's move that charge over here. Okay, we've got 2 permanganates, and let's see what we have on the other side. On the other side, we have this manganese 4 oxide, and we note that, oh, this 2 looks kind of funny now. We note that it's a solid, so we don't break it up. Okay, it's not aqueous, we don't break it up. So this is an insoluble compound, it turns out. A lot of oxides are water insoluble. So anyway, now we look at this compound. It's just a normal covalent compound, so we don't break it up either. Okay, so we've got our compound there, which also dissolves in water. And now we've got, okay, so we've got hydroxides. Now it turns out a lot of hydroxides are insoluble, but a higher priority rule is that potassium salts are soluble. So we've got 2 potassium ions, and then we look and we're going to have 2 hydroxide ions, also aqueous. Okay, so now we're done. So this is the full ionic equation. So the nice thing about the full ionic equation is that it shows you what's floating around in your beaker, right? This is actually, these ions are floating around separately from these ions at the end, and at the start we've got these ions floating around separately. But some of the ions aren't really doing much. So we like to sometimes cancel the ones who are spectator ions just so that we can, so let's turn this into a net ionic equation. And we just do that by canceling stuff that's the same on either side. When we look at this, we see there's a potassium or 2 potassiums here that are aqueous, and there's 2 over there that are aqueous. So same compound, same physical state, we can cancel it. And we have to make sure there's 2 there and 2 there, so we cancel the same amount. We look for anything else we can cancel. And, well, there really isn't anything else we can cancel, because we can't cancel the permanganates because those got reduced from a plus, the manganese went from +7 to +2. So totally different compound, even though it's the same element. And the carbons are different on these 2 organic compounds, and indeed we went from water to a base, so we can't cancel anything else. So we could write this out again just a little more neatly and say we've got 4 waters, we've got 3 of our organic compounds as the reactant, we've got 2 permanganates. I didn't say this was aqueous, but it is. And then we've got 2 of the manganese 4 oxides in the solid form. We've got 3 of this compound here. Okay. Oops, that's supposed to be like that. Very good. And you might recognize this molecule, it's glycerin. And we've got 2 of the hydroxides. Okay, so you get the idea, right? This is a net ionic equation. So we've canceled the spectator ions. Okay, so in the net ionic equation, all the molecules that are shown actually get changed. Something happens to them. All the molecules and all the different ions get changed to some other form.